Hello all. In today's session we will execute the second exercise of your lab, that is design, train and test a multi-layer perceptron for tabular data and verify various activation functions and optimizers. That is, we will be designing a multi-layer neural network, train that neural network with some tabular data and test it by applying some activation functions and optimizers and compare the results with each activation function and optimizer, and these optimizers are used to reduce the loss function. So here you can create your own tabular data. I'll be using here diabetes dataset. So when I run this code and import the dataset, I'll get the path, and once I get the path, just have an idea of what the dataset contains is it has 768 rows and 9 columns, all numerical data. I'll use this tabular data for regression analysis and design, train and test using this data. I'll be designing a multi-layer perceptron model. So for that, I'll import modules to build this neural network. So first I'll be importing a sequential module which is used to build a linear stack of layers. A simple neural network with one layer followed by other is called as a sequential neural network. So first I'll be importing that. Next I'll import dense module. Dense module which will be considered as a key component of multi-layer perceptron model, and it is used to build a fully connected layer. How many layers and how many neurons in each layer will be decided once we start writing the command. And then we'll be talking about the optimizers. So we will import all the optimizers which will be used here. We have talked about stochastic gradient descent in the theory sessions. These are the other two optimizers. You have many more. I'll be using only these three optimizers here. In stochastic gradient descent, you can see that we have many zigzag variations of updating weights to reach the minimum value or the goal weight. So to avoid those zigzag motions, which are nothing but called as noises, we introduce momentum. So that reduction of those noise in SGD can be done by using another kind of optimizers called as ADAM, which is nothing but adaptive momentum optimizer, and RMS prop represents the root mean square propagation optimizer. We also have ADAGRAD, which is adaptive gradient. You can add that optimizer also in this. Next I will import the dataset. I will import train test split, and then I will import the standard scaler which is used to normalize the data, numerical data what you are using. That will be normalized with mean value as 0 and variance as 1. Next I need to evaluate the model, so I will be importing this loss function called as MSE. As it is regression analysis, I'll use MSE, and then I'll plot the evaluated model. So first I load the data. To load the data, I use variable called as data, load diabetes. X is all the input features, Y represents the target values. Next I will standardize the data by creating an instance, and then standardize all the values of X, that is all the input variables will be standardized, nothing but called as normalized. Next I will split the data set with 20% of testing and remaining 80% for training. Here I will be defining the model. For that I will create model, a function with predefined activation function as ReLU and optimizer as ADAM, and then a function called as sequential also will be generated, which will initialize sequential model with a linear stack of layers. How many layers and all? So I will be creating 3 layer data. One is for input, 2 hidden layers, and the third layer is nothing but my output layer. So the first hidden layer with the dense 64 units. So it will add a dense layer with 64 units, and I'll take the input shape as same as that of the X training data, and activation function is the parameter. Next I will add another dense layer with 32 units, which is my second hidden layer, and the same activation function, and the output layer with 1 unit, no activation function because it is regression analysis where the output will be a continuous value. Next I will compile it. Model.compile with the optimizer, and the loss function what I am using here is mean squared error. Next I will define all the activation functions to be replaced here and all the optimizers, and store that MSC value of each activation with optimizer in a dictionary called as results. Next I will train and test the model with the different activation functions and optimizers. So I'll create a loop here. Outer loop has activation functions and the inner loop will have optimizers. And then I'll call up create model function, which was already called here, with activation function and optimizer, and fit that with 100 epochs. So model gets trained for 100 epochs, and model should update the weights after every batch size, which is 32. I'll evaluate the model using the MSC be the loss function which I'll be using here to evaluate the model. That is, for each activation function and optimizer, I'll calculate the MSC for the neural network what I have designed with 3 layers. First is input layer, second and third are hidden layers with 64 and 32 units respectively, and the last is 1 unit output layer. And I'll be plotting the figure with the different MSC values of all the activation functions and their optimizers. So you can see the output here for ReLU activation function. When I am applying Adam as an optimizer, this is the MSC, and so on. What do you notice here is I get an NAN value, not a number value, when I am using activation function as ReLU and SGD as my optimizer. So in that case, what will I do is I will reduce the learning rate, or I can update the weights, learning weights. So might be due to convergence, this MSC value we didn't get any MSC value here. So in the graph also you can see that I didn't get ReLU graph. I got graph for tan H and sigmoid for all the 3 optimizers. So this is the output of the dictionary results with all the activation function, optimizers and their MSC values. So NAN is the MSC value. So I can change this NAN value by varying the learning rate. So for SGD and ReLU activation function, I have reduced the learning rate. Earlier it was 0.01, now it is 0.0001. And when I run this code, I got ReLU SGD optimizer MSC as 6797. So the same I'll add up in the previous coding, where I have just introduced the learning rate for SGD. You can see here, reduce the learning rate, and here I have added up one more optimizer called as AdaGrad, which is nothing but adaptive gradient, which will adapt the gradient values depending upon the loss function. And when I run this code, you can see the outputs here. MSC for ReLU and SGD also, I got some value. Earlier it was NAN. And this is the graph of different activation functions and optimizers MSC value. And you can notice that SGD with the tan H activation function is having minimum error. So tan H activation function with SGD optimizer can be used for this data set. So this is, we have designed a 3-layer neural network for regression analysis of diabetes data set, and we have found that ReLU activation function with the stochastic gradient descent optimizer is better as it has minimum MSC value. Sorry, tan H with SGD, this one. Tan H with SGD is having minimum MSC value. So tan H with SGD is better for our diabetes data set to reduce the loss function. Thank you all.